I'm Sina Sharifi, a PhD student at the EC department of Johns Hopkins University, and I'm here to present our recent work on bilevel optimization. This is a joint work with Erfan Yazdandoost from the University of Arizona and my advisor Mahyar Fazlyab. A bilevel problem consists of one optimization problem embedded inside the constraints of another. The upper level problem chooses x to minimize an outer objective, but the variable y must come from solving a second optimization problem at the lower level. The diagram illustrates this hierarchical relationship. For each value of x chosen at the upper level, the lower level solves its own optimization problem and returns a corresponding y. This coupling between the two levels creates a highly nonlinear dependency. Bilevel optimization is inherently non-convex, even if both the upper level and lower level objectives are strongly convex in their own variables. Our goal in this work is to use tools from control theory to design efficient and reliable algorithms for solving this class of optimization problems. Bilevel optimization appears in a wide range of domains, from machine learning and transportation to energy systems and robotics. Here, I highlight two concrete examples. In the case of electricity market, we have independent system operators that have a specific objective or goal in mind. For example, here we assume that they want to ensure that enough capacity is procured during a capacity auction. With this goal, they have access to a set of market parameters that we denote by theta. When the lower level problem receives these parameters, the capacity market is run, where the generators will bid, and then the market is cleared and a set of prices is obtained. This shows how the two levels interact together. A second example comes from robotics, specifically gate optimization. Here, the lower level solves a parameterized MPC problem to generate control inputs for the robot. The upper level then adjusts the MPC problem, for example, step length, timing, or cost weights, to produce an efficient and stable gate pattern. Again, the upper level decisions shape the lower level control problem, and the outcomes of the control problem feed back into the optimization loop. Now, we formally state the assumptions we work with. We assume that both functions f and g are twice differentiable, Lipschitz continuous, and have Lipschitz gradients. We also assume that g is strongly convex. Importantly, we do allow f to be non-convex. Under these assumptions, the lower level problem has a unique solution, which we denote by y star of x. This allows us to simplify the bilevel problem into a single level formulation. We define an implicit objective function L of x, which is simply f evaluated at x and the corresponding lower level solution y star of x. The outer level problem then becomes minimizing this implicit function. Once we define the implicit objective L of x, the most straightforward approach is simply to run gradient descent on this function. To do that, we need the gradient of L, which is often called the hypergradient. Using the chain rule, we can express this hypergradient in terms of the derivatives of f and g along with the optimal lower level solution. However, computing these quantities is expensive for two main reasons. First, we need to solve the lower level problem at every iteration in order to obtain y star of x. Second, the hypergradient formula involves inverting the Hessian of g with respect to the lower level variable, which can be costly or unstable in high dimensions. These two operations make the mainstream approach difficult to scale and motivate the need for more efficient alternatives. We introduce a new framework for solving bilevel optimization problems, which is inspired by recent control theoretic approaches to optimization. The starting point is a gradient flow dynamical system that focuses only on the upper level objective. At this stage, we intentionally ignored the constraints that come from the lower level problem. The key idea is that we can then use tools from control theory, specifically the notion of set invariance and control barrier functions, to enforce the structure imposed by the lower level. We do this by designing what we call a safety filter. The filter is formulated as a convex quadratic program, and its role is to minimally adjust the gradient flow dynamics so that the trajectory always respects the optimality condition of the lower level problem. I will explain the design of this safety filter in detail in the next slides. The slide presents the construction of the safe gradient flow, or SGF. We encode the lower level optimality condition by defining h of x and y as the gradient of g with respect to y. When h equals to 0, the lower level problem is solved. Our goal is to keep the system on the manifold where h equals 0. To do this, we enforce h to contract to 0 exponentially. This gives us a differential condition that relates the velocities of x and y. When we expand this condition, we obtain an affine constraint involving the mixed partials and the Hessian of G. We now take the unconstrained gradient flow for minimizing the upper level objective and filter it through a quadratic program. The QP selects the velocities that stays as close as possible to the negative gradient of f while still satisfying the contraction constraints. The solution of this QP defines our safe gradient flow. A key advantage of this approach is that we never need to compute the exact lower level solution y star of x. The QP, despite having a closed form solution, requires inverting an m by m matrix. Our previous version of the safe gradient flow enforced the lower level optimality condition through m equality constraints, one for each component of the gradient with respect to y. The key observation is that instead of enforcing m separate constraints, we can combine them into a single scalar condition. We do this by requiring that the square norm of the gradient of g with respect to y be equal to 0. This defines the same solution set, but in a much more compact form. When we enforce only this single constraint, the corresponding safety filter no longer requires inverting an m by m matrix, which removes one of the main computational bottlenecks. However, using the squared norm constraints introduce a new challenge. At points when the gradient of g with respect to y is 0, the resulting dynamics for x and y can become discontinuous. This can cause instability or poor numerical behavior. To address this issue, we relax the strict equality constraint imposed by the lower level problem and use control barrier functions. The idea is to relax the strict lower level optimality condition. Instead of forcing the gradient of g with respect to y be exactly 0, we allow it to be within a tolerance. We define a set L epsilon squared of h, which consists of all points where squared norm of the gradient is less than or equal to epsilon squared. This gives us a controlled amount of lower level suboptimality that we are willing to tolerate. To make sure the trajectory never leaves this relaxed set, we use a control barrier function. The barrier condition on h enforces forward invariance. Once the system enters the safe set, it stays there for all future times. We then incorporate this constraint into the safe gradient flow by solving a quadratic program. The QP finds the closest feasible velocity to the negative gradient of f while satisfying the barrier condition. Importantly, this QP has a closed form solution. It does not require inverting any matrices, and unlike the earlier squared norm formulation, it produces continuous dynamics even when the gradient of g is 0. Together, these properties make the inversion-free safe gradient flow both scalable and numerically stable. In our prior work from ACC 2025, we showed that the temporal average of the hypergradient converges to an epsilon neighborhood of 0 with the convergence rate of 1 over t. Since epsilon is a design parameter, we can make the steady-state error arbitrarily small. Up to this point, our method has been described entirely in continuous time. However, continuous time solvers are not practical for high-dimensional problems, so we need to discretize the dynamics. The most natural choice is the forward Euler discretization shown at the top. Here, z simply stacks together x and y, and g defines the safe gradient flow direction determined by our quadratic program. However, this discretization introduces a non-trivial challenge. For a given iterate, there may not exist any positive step size that simultaneously satisfies the safety condition. The figure on the right illustrates this issue. If the current iterate is on the boundary, the search direction can become tangent to the boundary, implying that the discretized step may violate the constraints set for any positive step size. To address the discretization challenge, we introduce a new type of safety filter that is explicitly designed for discrete time updates. Instead of the earlier QP used in the continuous time, we now formulate a convex QCQP that directly solves for the update direction delta z. The key feature of this QCQP is the additional tilting term in the constraints shown in yellow. Geometrically, this term biases the update direction towards the interior of the safe set rather than allowing it to become tangent to the boundary. This ensures that a positive step size always exists, even after discretization. It is important to note that the QCQP still has a closed form solution, so it adds no computational overhead. The remaining question, which we will answer next, is how to choose the step size t at each iteration once we have the update direction. Once we compute the update direction from the QCQP, the remaining question is how to choose the step size that is both safe and effective. To address this, we design a backtracking line search procedure that enforces two conditions simultaneously. First is the classical Armijo condition from optimization. This condition ensures that the upper level objective decreases sufficiently along the direction delta z. If the condition is not satisfied, we shrink the step size. The second requirement is safety. We must ensure that the discrete time iterates remains inside the relaxed safe set. This is done by imposing a discrete time forward invariance condition. The line search starts from an initial step size and repeatedly reduces it until both conditions hold. The resulting step size ensures progress on the upper level objective while also guaranteeing that the method remains feasible at every iteration. This gives us a fully discrete, anytime feasible, safe bilevel optimization algorithm. To establish theoretical guarantees, we begin by outlining the technical assumptions. We assume that both f and g are twice differentiable and locally smooth. Instead of assuming strong convexity of the lower level problem, which can be restrictive, we impose a weaker condition. The function h acts as a regular barrier function. This means that h equals 0 if and only if its gradient is also 0. We also assume that h is coercive, ensuring that trajectories cannot escape to infinity. Under these assumptions, if the current iterate lies in the relaxed safe set, the following properties hold. First, the QCQP is always strictly feasible. Second, the search direction is guaranteed to be a descent direction for f. Third, the proposed line search ensures forward invariance. That is, if we start inside the relaxed safe set, all subsequent iterations stay inside of it. Finally, when the QCQP returns a zero direction, this exactly corresponds to a point that satisfies the KKT conditions of the underlying bilevel problem. Together, these results show that the algorithm is well posed, makes progress on the objective, maintains feasibility, and converges to a meaningful solution. We now present the main convergence guarantees of our discrete time algorithm. We assume that the initial point lies in the relaxed safe set. Under this assumption, the first result establishes that the line search always returns a step size that is uniformly bounded away from 0. The key takeaway is that the algorithm never gets stuck with vanishingly small step sizes thanks to the tilting parameter w that we introduced. The second result shows that the safety constraint function contracts geometrically at every iteration. Since this term is non-positive inside the safe set, the inequality guarantees that all future iterates remain feasible. This is the discrete time version of forward invariance. Finally, we prove that the average squared norm of the update direction converges to 0 at a rate of 1 over k. This is analogous to standard guarantees for non-convex first-order methods, but here it applies to a bilevel optimization problem. The result also implies that the update vanishes asymptotically, meaning that the algorithm approaches to a stationary point of the relaxed problem. Together, these results show that the method is safe, stable, and provably convergent in discrete time. In our experimental evaluation, we consider the data hypercleaning problem, which is a standard bilevel benchmark. The idea is to learn a set of sample weights that suppresses mislabeled or low-quality training data so that the resulting model performs better on a clean validation set. The upper-level objective evaluates the model on the validation data using the parameters that result from solving the lower-level problem. The lower level trains the model using weighted cross-entropy loss, where the weights are obtained by applying a sigmoid function to the hyperparameter vector x. A quadratic regularizer is also applied to the model parameters to prevent overfitting. This setup reflects a realistic and challenging bilevel learning scenario because the lower level optimization corresponds to full neural network training and the upper level adjusts sample weights indirectly through y star of x. The left figure tracks the validation loss over iterations where our method shows a clear and stable descent. The middle figure reports test accuracy showing consistent improvement as the algorithm progresses. The right plot shows the norm of the update direction delta z decreasing, indicating convergence. Overall, the results confirm that our discrete safe bilevel optimization method is stable, effective, and competitive on a non-trivial machine learning task. Thank you for your attention. The QR codes for the GitHub repository and the papers on archive are available here. Please reach out via email if you have any questions. Thank you.